And the first speaker of today will be Junsei Tokuda from IBS. Please.
Okay, thank you for introduction. My name is Junsei Tokuda from IBS in Korea. And first, I would like to thank organizers for inviting me to have a talk here. And today's talk is based on these papers in collaboration with Katsuki Aoki, Shinichi Hirano, Turan Lok, Toshifumi Naomi, and Sota Sato, and actually many collaborators, Ryo Saito, Satoshi Shirai, and Masahito Yamazaki. And today's main topic is about the swampland program. Oh, it doesn't move. Oh, sorry. Oh, okay. And the main question, which may be answered by swampland program will be that what the quantum gravity theory is. Of course, to answer this question, we need predictions which can be tested experimentally, and it will be very difficult because the Planck scale, the typical energy scale of quantum gravity, is given by Planck scale, which is much higher than the experimentally probable scale. But this situation may be much improved if the quantum gravity have some hidden predictions on low energy effective theories. And this is a main motivation for swampland program. And the main statement would be that not all consistent looking EFTs are consistent with quantum gravity, and inconsistent EFTs are said to be in the swampland. And this kind of hidden predictions of UV complete theories has been known in the context without gravity. And one of such predictions are given by the positivity bands that are formulated in terms of S matrix. And actually, this is the main topic of today's talk. And the derivation of positivity bounds are based on the S matrix unitarity, analyticity, and so on, some nice properties. And the statement is that if you consider, for example, the effective theory for photon, whose Lagrangian is given by this form, so F2 fourth term is the leading order higher derivative terms. Then the positivity bound states that this coefficient C2 must be positive definite. And from low energy EFT perspective, we simply write down all the allowed operators which are allowed by symmetry. And we don't need to care about the sign, but positivity says that its sign must be positive. So in this sense, it is the hidden predictions of UV completion. Then it would be natural to ask if we can extend the positivity bounds to the gravitational context. Then if we can extend it, then it may be useful to derive the swampland conditions. But if the derived conditions are not so interesting, then it's kind of disappointing. So it would be also important to ask if we can extend it, then does it give any interesting swampland conditions phenomenologically? Phenomenologically interesting conditions. These questions are the questions I would like to address today. And this is the today's talk plan. The first, I would like to review the conventional positivity bounds without gravity. And then I would like to move to our works, where first I would like to explain the formulation of gravitational positivity bounds. And then I will discuss the implications for the models. Today I focus on the standard model and the dark sector physics. And particularly I will focus on the dark photon models today. Okay, so let me start from reviewing the conventional positivity bounds without gravity. And as I said, it is formulated in terms of scattering amplitudes, and actually 2 scattering amplitudes. And because I will later consider the 4 photon amplitudes, so from now let's consider 4 photon amplitudes. And that is written by M of ST. So S and T is our usual Mandelstam variables. S is central mass energy squared, and T is momentum transfer squared. And the essential point of positivity bounds is that in the UV complete theory, the amplitude must behaves well at high energies. And here is the example where the UV complete theory is given by QED, and EFT is given by this Lagrangian with this leading order higher derivative terms. And then at low energies, the 4 photon process is described by this contact vortex in contact diagrams, which grows as fast as a square at high energies. So the growth rate is high, very fast. But in the QED, this process is embedded into this box diagrams, whose growth rate is now improved. It is given by log square. So then the question is how this badly behaved amplitudes can be embedded into the nice UV complete amplitudes. And positivity bound states that this embedding is possible if and only if the C2 coefficient here must be positive. And this condition can be derived from the simple complex analysis. So let me explain this in this slide. So we assume the analyticity of the amplitudes in the forward limit, except for usual poles and cuts. The cuts is given by the electron box diagram, some multi-particle states. And then we consider a complex integral of amplitudes divided by S cube. And first, the contour is given by this blue circle that is localized in a very low energy regimes. So this is complex S-plane. So this is very low energy regimes. Energy scale is lower than the electron. And then this is calculable, EFT calculable. And more precisely, this quantity corresponds to C2 defined here, defined as a series coefficient of a square when we perform the series expansion of amplitudes at S equals 0. And thanks to the analyticity, we can consider contour deformation without changing the value of the integral. So now the blue circle is now deformed to the green infinitely large circle plus the pink lines. These are cut lines along the branch cuts. And the contribution from these, each component is given by like this. And the first one is contribution from the cuts that is given by the imaginary part integral. And the second term represents the contribution from infinity. Because the right-hand side contains the behavior at large S, large energy. So without knowledge of UV completion, we cannot calculate explicitly. But by imposing the unitarity on UV completion, then we can say that the first term must be positive. This is the consequence of the optical theorem. And the second term can be shown to be 0 thanks to the locality constraints, or so-called Froissart-Martin bounds. Then we can conclude that the left-hand side must be positive definite. This is the conventional positivity bounds. And more recently, okay, so let me summarize. This is the positivity bounds, the sum rule for C2. And more recently, it has been pointed out that it would be useful to separate the EFT piece and the high energy piece by defining this quantity C2 of lambda. Here, the lambda is defined as a cutoff scale of EFT. So then by definition, the imaginary part integral from low energy scale up to cutoff scale of EFT is calculable using EFT. So C2 lambda is also calculable. And then the sum rule for C2 lambda is given by this. And then the right-hand side is still positive definite. So we can derive the positivity for C2 of lambda. This is so-called, sometimes called improved positivity bounds. This is a conventional positivity bounds without gravity. Now let me move on to the gravitational part. So first I would like to explain formulations, and then I will discuss applications. Okay. So first, the extension to gravity is in some sense trivially non-trivial, because the property of quantum gravity S matrix is not fully understood because the quantum gravity is not fully understood. Of course, there is some attempt to prove to reveal the properties of quantum gravity S matrix, but still not fully understood. And there's also an important feature that is that the T-channel graviton exchange diagram grows as fast as a square. So these diagrams. So in the derivation of positivity bounds, we use the S-square boundedness at infinity, but this diagrams violate that. So this is another important feature. But we may expect that in the UV complete theory, the behavior of amplitudes becomes milder. So then let's suppose that the behavior of amplitudes becomes mild at high energies to satisfy this S-square boundedness in the physical domain, which is indeed realized and satisfied by the explicit string amplitudes. And actually, this is the kind of a starting assumption in the S-matrix bootstrap program. And then starting from this assumption, we can discuss how the discussion of positivity bounds changed. And thanks to this assumption, then we can now derive the sum rule for C2 lambda. But the sum rule for C2 lambda is still non-trivial because it contains the graviton T-channel pole. So this is an expression of sum rules. So here the 1 over T pole, graviton T pole appears. This is because in the sum rule, we can relate the coefficient of S square to the imaginary integral of imaginary parts. But now the graviton, because the graviton is a spin 2, so it also contributes to the S square coefficient. So this also appears, 1 over T pole appears in the sum rule. And then in order to use the optical theorem, positivity of imaginary parts, we need to take the forward limit. But if we take this limit, then this part becomes divergent. So then from the regularity, we know that the left-hand side is regular. This means that some cancellation should occur, but we don't know the remaining term is positive definite or not. And one solution has been proposed by this paper. They propose to consider sum rules away from the forward limit because the forward limit is problematic. So their strategy is that to perform the smearing in T to localize the sum rule in the domain around some negative regions. In that case, it's given by the location of branch cuts. And this is equivalent to working impact parameter space, which is smaller than the Compton wavelengths of some lightest particles. But unfortunately, they are bound technically, because of some technical reasons, they are bound suffer from IR divergence in 4 dimensions. Here is IR cutoff. So today I would like to discuss another solution. This is which is proposed by us in 2020. The main point is that the graviton 1 over T pole is in the sum rule is cancelled due to the Regge behavior of this form, which is realized in the tree-level string amplitudes. So this statement can be easily understood. So by substituting this Regge behavior ansatz into this imaginary part integral, and so here I substitute it, and then this integral is simply calculated. And we can easily check that this part reproduces the 1 over T pole. Then by choosing the F0, the value of F appropriately, we can cancel the 1 over T pole. And we can also calculate the finite piece. And this is an easy calculation, and we can derive the sum gravitational positivity bounds, gravitational sum rule for C2. And this is the expression. And the first term is the positive definite. And the second term is a finite term, which appears after the cancellation of 1 over T pole. An important point, and this important point is that this part is actually negative due to unitarity. So we can derive the lower bound on this by this. The M, capital scale of M, is determined by the second term. So this is, since this Ft is parameterizes the Regge behavior. So scale M depends on details of the Regge behavior. And also the important point is that because of this negative term, the right-hand side can be in general negative. So the exactly 0 C2 is allowed. And this is indeed realized by the type 2 dilaton supersonic amplitudes. And one important point of this expression is, that because the C2 lambda is EFT calculable, and the right-hand side is given by the details of Regge behavior, which is depends on the detail of UV completion. So this provides an explicit relation between EFT and quantum gravity. And so for example, if we observe the violation of C2 of positivity of C2 in models, then this means that the observed negativity must be explained by the detailed UV properties of S matrix, such as details of Regge behavior. So in this perspective, it is important to check the consequence of the positivity of C2 for constraining the UV properties of S matrix from low energy observables. So today, from now on, I would like to discuss the implications of this inequality from detailed concrete models. And first, I would like to discuss the standard model. So this is so we focus on the 4-photon process in the standard model coupled with gravity. So Lagrangian is given by this. And in general, we can also have higher derivative terms, but we ignore such terms for simplicity because it doesn't change the essence. So today I would like to ignore them. And actually, this kind of analysis is performed for different systems, such as QED plus gravity or QED-like system with gravity. But today I will not introduce such papers. And then what we have to do is just compute the C2 lambda by computing the amplitudes in this model, standard model coupled with gravity, and then discuss the implications of this inequality. That's all. So here, let me remind you the definition of C2 lambda. So C2 lambda is EFT calculable and is defined by this inequality, defined by this. And C2 is the S-square coefficient. And lambda is the EFT cutoff. And also we assume that the UV completion is weakly coupled. So we evaluate the C2 up to 1 over m Planck square, and we ignore the higher order graviton terms in 1 over m Planck in this analysis. So we ignore the graviton loop corrections. Okay, so let me explain how to calculate C2 lambda. And so in general, we can decompose the C2 lambda into 2 pieces. The first piece is a non-gravitational piece, which is contributions from processes without graviton. And the gravitational part represents a contribution from processes with graviton. So non-gravitational part is, for example, given by these diagrams, 2 electron box diagrams or double boson loop diagrams, or possible QCD contributions, for example. So in these diagrams, the gravity is not included. So it's just a standard model diagram processes, while the gravitational part includes the graviton exchange. So for example, we can consider this kind of process. So the photon graviton process 3-point vertex is corrected by the electron loops. Actually, this diagram is very important. So let me first show the calculation of non-gravitational piece. So to calculate the non-gravitational piece, it is important to notice that the non-gravitational amplitudes is given by purely the standard model. So that amplitude satisfies the very nice properties So it satisfies the twice subtracted dispersion relation. So we can calculate the non-gravitational piece by simply evaluating this integral that is given by the total cross section. And then for QED process, this is the total cross section for. So here I suppress the overall some coefficients for simplicity. But anyway, so for QED process, this total cross section is at high energy is evaluated by this, suppressed by coupling constant, and also suppressed by 1/s at high energies. Although for weak interactions, the weak boson loops provides this constant total cross section. So MW is a weak boson mass, and then if the non-gravitational contribution from electroweak sector is given by this QED process and weak boson loops. And then if we assume that the cutoff scale is much higher than the electroweak scale, then the second term dominates. So this is because the spin 1 exchange becomes important at high energies, because the total cross section is dominated by this one. The electron box is much suppressed. So next we explain the QCD contributions. So since we consider physics in the forward limit, so IR physics can play a role, even though we consider high energy amplitudes. And particularly to calculate the high energy amplitudes, the Reggeization theory is useful. And actually, by using Reggeization theory, we can estimate the QCD contributions. And QCD gives dominant contributions via the T-channel Pomeroy exchange. The schematic picture is given by this. The photon is converted into vector mesons, and then the vector meson scattering is mediated by the T-channel Pomeroy exchange. And in this way, the for photon amplitude is dominated by this non-part of the QCD contributions. And then the total cross-section is estimated by this. And actually, this behavior is based on the observation based on some experiments, but and its contribution to photon process is evaluated in this paper, and we extrapolated their results up to high energies. So around the cutoff scale of EFT, which is we will later take it to be some gut scale. So this is kind of extrapolations. And once adapting these extrapolations, the non-gravitational piece can be calculated like this. And next, for gravitational piece, the electron one loop contribution to gamma H couplings gives the dominant contributions. And this is simply because the electron is light. So in the forward limit, amplitude for this process is given by this. When we perform the T over M electron mass expansions, at the leading order is given by this term. So since this term grows as fast as S square, so it can contribute to the S square coefficient. And so gravitational piece is given by this. And now we investigate this behavior. Sorry, this part is 0, sorry. And then the non-gravitational piece is given by first 3 terms, while the 4th term is gravitational piece. And only the 4th term, gravitational piece is negative. So this inequality becomes non-trivial. And by substituting the real, and each contribution is plotted in this way, plotted in this figure. And QED process, the horizontal axis is lambda, and the vertical axis is this part. And the black dotted line is minus gravitational part. So it's because grav is positive, not negative. And then this figure shows that the QCD contribution dominates at large lambda. And when lambda is around 10 to 16 Jeff, the QCD part is comparable to grav. So this inequality is saturated. So we get these bounds. So this means that the standard model can easily satisfy our bounds. Okay, so next let's consider the dark photon model. And for simplicity, we consider a hidden U1 massive gauge field, A prime, which is kinetically mixed with the ordinary photons. And kinetic mixing parameter is given by epsilon. And that kinetic mixing can be easily generated by if we have some heavy particle, which is charged under both of U1. And then by diagonalizing the kinetic term, we get the dark photon A prime is coupled to the standard model charged current, but the coupling is suppressed by kinetic mixing parameters. And in this setup, let us consider the photon, dark photon, photon, dark photon process. And for simplicity, we ignore QCD sector. And then what we have to do is the same as in the standard model. And sorry, again, this right-hand side is 0, sorry. And then the first term is the contribution from the weak boson loops. As in the case of standard model, when we ignore the QCD, the weak boson loops dominates the non-gravitational piece, while the gravitational piece is dominated by the electron loop again. So then we can discuss this inequality. But for dark photon case, since we consider a massive dark photon, in that case, the longitudinal mode scattering of longitudinally polarized dark photon can be also considered. And if we consider such process, then we have this additional suppression factor in the non-gravitational piece. And this simply represents the decoupling of longitudinal modes in the massless limit. And then we can plot the implication of these bounds. And the black shaded regions are actually the region below this line. These lines are excluded by our bounds. And so the white line is a bound from longitudinal modes, so it's extremely strong. So important message in this slide is that we can obtain, in general, the testable lower bound on the kinetic mixing parameter in this model. And since the experiment provides a lower bound on the upper bound on epsilon, but our bound provides a lower bound, so it's complementary to experimental research. And also our bound becomes very strong for small MA prime, so the lower bound on the mass is suggested. But the one important remark is that if we have a new particles mediating this process, then the result will be changed. But I think the time is running, so let me briefly explain. So for example, if we consider a vector bosons V charged under both U1s, then for example, for longitudinal scatterings, now the process mediated by the vector boson is the dominant one. And now this process is not suppressed by kinetic mixing parameter. So actually in this setup, we have no lower bound on the kinetic mixing parameter, but still the resultant bound looks like this. And for tiny dark photon mass, the cutoff scale becomes very tiny. So again, in this model, the very tiny mass is disfavored. This is because the non-gravitational piece vanishes in the massless limit. And this suppression may be absent if we consider a scenario where the mass term of the dark photon is generated by the Higgs mechanism, and such process is considered in these new papers. But still, the complete study is still in progress and not finished. So let me summarize my talk. So gravitational positivity bounds reveal the UV-IR correlations. Particularly, we can derive the approximate positivity. And scale M depends on the details of UV theory. For example, in the scenario where the amplitude is Reggeized, this is given by the details of the Regge behavior. And then we discuss the implications of this inequality for models, and we find that the standard model easily satisfies the bound, but we find a very strong bounds for simplest dark photon models, and the bounds are complementary to experimental research, and this suggests the possibility to experimentally probe the quantum gravity. And our work, the main conclusion of our work is that the further study of quantum gravitational matrix is important for dark sector phenomenology and vice versa. So Thank you very much.
Thank you, Junsei. Do we have questions?
Yes, may I ask something?
Yes, please.
So I'm slightly confused about your argument with using the Pomeron. I mean, the Pomeron with its intercept 0.08 violates the Froissart bound, which I think is sacred because you take unitarity to be sacred. So I wonder whether you have any right to extrapolate to the Pomeron, which violates, I think it violates the Froissart bound to such high energies.
So thanks. So actually, yeah, that's point. And yeah, because this 0.08 is a kind of fit, experimental fit for kind of phenomenon. So it's dangerous to extrapolate this to arbitrary high energies. So yeah, actually for simplicity, I just explained this. But actually in our paper, we adopt several models. For example, we assume that this exponent is saturated to how to say, it becomes Froissart type bounds, log S squared. We also consider extrapolation with linear. So in that case, exponent becomes 0 in the high energy limit. Or we adopt several models for extrapolations actually. And yeah. And result actually unchanged.
That's fine. May I ask another question about the dark photons? Yes. I thought you were bounding the F to the 4 term. I didn't understand how you managed to bound the mixing, which is not a scattering process, but a kinetic, I mean, leading order kinetic term, basically. I mean, your arguments before were always about scattering, but the mixing is not a scattering process. So I didn't understand how you bound the mixing parameter. Can you just say it again?
So maybe I don't understand the point, but let me explain. So here we consider the 4 photon, not 4 photon process, but the gamma prime process.
Right.
So then this kinetic mix, if we have kinetic mixing, then after diagonalizing the kinetic term, the dark photon is interacted with the standard model charge current. And it is suppressed by epsilon. And then this is the leading important diagrams. And the gamma prime is a dark photon. And then this vertex, the gamma prime interaction between dark photon and standard model current, such as double boson, is suppressed by kinetic mixing parameters. So we have a suppression by kinetic mixing parameters here. And this is the reason why we get the bound on the kinetic mixing parameter.
But you can if you have no charged particles, for example, you can always exactly demix, right? I mean, you can just choose a basis where things don't mix. How does it fit your analysis? I mean,
I'm really sorry, but we are running a bit out of time. So maybe we can keep the discussion after the second talk, if it's fine for you, if you have a quick answer.
Sorry.
I'm really sorry, but we should start with the monkey. We are already late, but you can keep discussing after monkey. It was very interesting. Thank you.
Okay, thank you.